Good morning, everyone. My name is John Aycock from the University of Calgary, and I'll be chairing this session today. So our first speakers, I tell you, I was shocked to learn that home network devices might not be secure. And our first speakers are going to tell us all about that, Pavel Sramek and Martin Smarda.
Good morning, ladies and gentlemen. I'm Martin, my colleague here is Pavel. We are working at Avast Virus Lab now for some 3 years. And we would like to tell you something about our latest project, which is trying to address problem of insecurity of home network devices. We have already heard several excellent talks about those issues. So we want to propose a solution. I would like to start with a question. Can you guess what this is? Obviously, it's a light bulb, but not an ordinary one. This one is special. This is the oldest shining light bulb in the world. It's supposed to shine since 1901. But the time goes quickly, evolution progress. So our current light bulbs, which you can buy at the market, have Wi-Fi connection to your mobile phone, and through that app, you can control its color, its intensity. It means that the processor in this light bulb is a small computer, which certainly brings us new security issues. I would like to tell you a short story about development of home networks. At the beginning, the first time we can consider it a network, there's a direct connection from the internet to your router and to your computer. Accessories are connected to the computer via USB. And there are attacks. There are attacks on the computer, not at the infrastructure. But our products and antiviruses are there to stop those attacks. The network grows. We are getting more devices, cell phone, laptops, and they are getting attacked. And we move our presence there to protect them. But the story continues. The network is becoming more complex. We are getting smart TVs. We are getting networks attached storage. The USB printers became printers connected directly to the router, and they're starting attacks against those devices, and even the infrastructure itself. And not only directly through the internet, but as trampoline attacks from your computers. The question is, what can we do as an industry about that? Because we cannot install our products into TVs, obviously.
Now, since this is about the latest buzzword, the Internet of Things, I would like to make one thing clear. The things in the Internet of Things are not really things. They are still computers. Tiny embedded computers, but still computers with everything that makes them. Which means they usually run embedded Linux, and since most manufacturers want to get them out of the factory as quickly as possible, that Linux is usually close to the default settings of whatever the distribution they chose to base it on. Typically, they are controlled with a web-based user interface, since many of the things don't have a screen and a keyboard. But that obviously makes them need a web server for the web-based user interface. So they put a lightweight web server there, run CGI scripts or an arcane version of PHP, and call shell scripts from that, in some cases even under root. The manufacturers of those devices, at least in case of the cheaper ones, which make up most of the market, they see no need for additional security because since it's on the home network, that's supposed to be secure, so why bother, right? So there's usually no HTTPS, and the vendors usually don't even release firmware updates fixing security holes because they're already working on the next model down the line. Since their line of thought is, hey, they already bought that, no value in still meddling with it, we better make the next device work and ship it as soon as possible. That's obviously a huge flaw in how the industry works, but unfortunately that's the way it is. Here are examples of how bad guys are starting to abuse the fact that home devices are very poorly secured. What you see here is an example of what we call a trampoline attack. And it's a web-based malware from February this year. We call it HTML DNS changer, but it's actually both HTML and JavaScript. This malware gets loaded by the victim's browser, and that may be any browser, including an iPhone, and actually does not target the device which is running the browser. It targets the router. You can see that it tries to guess the address of the router, 192.168.1.1, and it tries to guess the username and password, in this case, admin. And what it actually does, it sends one HTTP GET request to change the router's DNS settings. And that's really the point for the attackers, because when they change the DNS on the router, then any traffic going through the router is going to be intercepted at the DNS level, which is enough for them to supply phishing pages instead of web banking, or to inject advertisements into any page that loads a common resource. Another kind of attack that targets home devices, or specifically routers in this case, is a direct one. And this is a very recent malware called PNScan. I will not go into detail of what the malware actually does, but the method it spreads by is, I would say, disheartening. It just scans a subset of the IPv4 public range and tries to connect via SSH. When it finds an open port, it tries totally bland default credentials, and unfortunately, sometimes it succeeds. Once installed, it opens a backdoor and scans another random part of the IPv4 range. So leaving SSH open to the wide area network port while still having default credentials on the box is very poor practice from the manufacturer to have this by default. Because if it wasn't default, this worm wouldn't have been so successful. Which brings me to the root issue for those two attacks. The passwords that are used to authenticate access to those devices have many problems. First, there are default pairs that are very easy to look up, and almost nobody changes them. Sometimes there are even backdoor pairs of default username and password, which are available but not mentioned in the user manual, and stay there even if the user changes it. But most users, even if they change their router password, they change it to a very poor one. Because, as we all know, there's a statistic of the 100 or 10 or 5 worst passwords ever that gets on the newspaper front page every quarter. It doesn't matter what are the hints for choosing the password. The user is going to choose 1, 2, 3, 4, 5 or password with a 0. And the malware writers know this and abuse this and try these weak passwords and succeed. What we believe causes this is the fact that the setup procedure for those devices is fundamentally flawed. The vendors, at least again in case of the cheaper end of the spectrum, do realize that setting up the router, changing settings, is a complicated task. So their solution is not to make it easy for the user. Their solution is to skip it at all and just tell the user to plug it in the wall and leave it on, running the defaults. This allows malware to try the defaults very easily. But why is it this way? I think there's a better way. If you buy a new Android phone, you take it out of the box, and it walks you through a very nice setup screen that helps you with security, tells you what's a strong password, and how to set up your account. Is there a problem having a 6-page wizard when you first turn on the router and connect to it via HTTP? I don't think so. It's just poor motivation on the vendor's part. That should be changed.
And it is not just a poor setup. It's a poor design of the system itself, mostly default Linux with open ports, These are statistics from routers we see in the wild. It's understandable it has HTTP port open. But why does it have Telnet, FTP, or SSH? It doesn't need them to function. And our preliminary scans shows that there are other issues, like open ports to the internet, probably hijacked DNS, poor settings at Wi-Fi without encryption or with very weak one. And there are vulnerabilities which can be easily exploited, for example, the famous one, ROM 0. To sum this up, the state of customer devices is not good. We are getting more devices with more vulnerabilities without updates, and the attacks are popping up. The attackers see value in these devices, and we should do something about that. We should try to change this state.
What we believe should be done first and foremost is raise user awareness that device insecurity is a thing. This was already mentioned here yesterday. People know that Windows PCs get viruses. People do not know that routers get attacked. And unfortunately, this carries on to the thinking of the manufacturers of those devices, and they do not care about security. What we want to propose is to detect the most common issues, including the bad passwords, including the bad security practice and the holes that that brings, and inform and educate the users about those security problems. The first step is making them know. Then we can offer them help to mitigate the problems if there is a solution available. And if it is an easy one, such as changing the password, we may even try to walk them through it. But the point is, we don't want to end up as secured as the bike in the picture. We don't want to overwhelm the users with constant notifications about incoming TCP SYN packets or whatever might be coming onto the network. We need some prioritization of what are the important issues. And ironically, the dark side is here to help us prioritize this. We should, of course, start with the issues that are being used for attacks. Now, since we can't install an antivirus software in a router or in a TV, at least not for now, we can't protect, we can prevent. So our proposed solution is to integrate an automated network security scanner in consumer antivirus and security solutions. We do not want to recreate professional network scanning tools. They're already light years ahead in how they scan the network and their databases, but they are not intended for home use. They are intended for professionals who know what securing a network means. They know what's a pen test. We want to address those people that don't even know they should secure their network, and that is what our tool targets. We want to offer them help with preventing the situation where they have open holes in their small network, and attackers are free to abuse them. We can detect those holes, and we can offer that education and help about them.
So, to scan for vulnerabilities, we need to know what to scan for. We decided to classify the vulnerabilities into 3 major groups. The first group in our beast zoo is bad configuration, weak cryptography, default settings. It's the best group from our point of view because it's easy to fix, usually. To fix it means to guide the user through settings and tell them how to change it. The second group is far more serious. They are device-specific vulnerabilities. They are errors which are specific for some model, for some manufacturer. They are usually not that widespread, but they are harder to fix because fixing them means disabling vulnerable services in better case, in worst case, patching the firmware of the device, which is a hard thing to do. Most common users don't have the skills to do that. and the patch is not always available. The last group is the vulnerabilities which get names, like ROM0, Shellshock, or other famous one. They are the most problematic because there are bugs in libraries or systems usually, and they affect the entire industry of devices. To fix them means to patch them with firmware update, which has to be released by all of the device vendors, which is not likely to happen. Scanning for these vulnerabilities is by nature algorithmic detection. We need to send some probe, and by the response we can judge whether there is a vulnerability or not. This brings us some pitfalls to avoid. For example, those probes can be destructive. We can send probe which may cause to reboot the device, even worse, which may to completely break it or break its settings, which is something we cannot do at our consumer network. So we need to be very careful which probes we send. There is an alternative. We can try a different approach by flagging the vulnerabilities in some table and searching it with vendor, device version, firmware version, but this is not that reliable solution. Other problem is utilization of network resources. We don't want to do a denial of service on our scanned network. So parallel probing may be a problem. We may float the devices which are created from cheap components and can barely handle the typical load. The other problem is we can hammer the device we are scanning itself. We can hammer the router itself, the network infrastructure. We want to avoid this problem. So we need to carefully balance our scanning efforts.
Yeah, just to add to that, the low-end devices barely have the computing power to do the job they were designed to do. If you try to guess passwords or send probes to whatever services are running, at the same time the user is trying to load a YouTube video, there's a very high chance that you will end up unintentionally DOSing the user's experience, which is, of course, bad. Now, to show an example of the probes that can be done easily and safely, by that I mean non-destructive and simple one request without hammering, we have the already mentioned famous ROM0 vulnerability. This is a vulnerability in the ROM pager web server by Allegro, and it manifests itself by this very simple loop where you, well, not a loop. It manifests itself as a response to a GET request to /ram-0, and this response is HTTP 200 OK code. And in the body of that HTTP response, there's the binary contents of a significant chunk of memory. Which means to probe for this, you just need to send one request and look at what you get. Usually, you expect a 404. If you get 200 in binary, that device is vulnerable to ROM0. Another simple one to check that's not based on HTTP is a lesser-known security hole in AntLabs devices. It's a misconfiguration issue in their embedded Linux, and it manifests itself by the fact that when you connect via the rsync protocol and navigate to the AntLabs folder on that device, what you actually get is read and write access to the root file system of the embedded Linux. That is, of course, trivial to check again, by just implementing a very small subset of rsync and looking at the results of opening the AntLabs folder. And both of those probes do not wreck the device. They leave it still usable and allow us to inform the user that there is a security problem that hackers can potentially abuse. Which brings me to the question of what to target. We want to target holes like this that are safe to check and affect a lot of users. ROM0 is a good example of that. As with everything, the 80-20 rule stands here. So that means that approximately 20% of security holes affect approximately 80% of the user base. That means we want to go after those few prominent holes that affect a lot of people first. And as I mentioned, the attackers already do that. They go after low-hanging fruit, so we should try to prevent them from doing it. How to achieve this? It's by having two feedback loops. The first outer one is having the scanner provide real-world telemetry back to our backend, of course, and using this telemetry to identify those 20% of highly prevalent and dangerous vulnerabilities, and prioritizing the implementation of the probes, because since they are algorithmic detections, someone has to write the code for them. The inner loop is prioritization in the engine itself, which means scanning the local network and only applying the probes that make sense for whatever is on the network. We're not going to try everything we have on every device, because that would run exactly into that unintentional denial of service issue on low-end devices and lengthen the scan.
So how does our scanning engine look like? After some starting event, which may be user interaction or just some timer, the engine first checks the device it's running on. We check the internet connection of the device, whether the connection is secure, whether it's, if it's via Wi-Fi, whether it's properly set up and encrypted. We check the DNS, whether it's likely to be hijacked or not. We check other stuff. Then we start to scan the network for the devices. This means we need to discover those devices by different methods like ARP scan or UPnP scan and other methods. But even this discovery gives us some interesting data, for example, MAC address of the device, which can tell us the manufacturer. Then we want to get more information about the device. If we want to scan the device, we get to know it first, and we need to get it know well. So we are trying to get as much information as we can about which services are running there, which ports are open, and other stuff like that. This information helps us to choose which detection probes to perform in order to be fast and not to harm the device. So we send our detection probes, we get our responses, and we take the data we get. We do that for all the devices we found on the network, or for the devices we consider important, and we report the state to the user. If there is a vulnerability found, we report it. As we mentioned, we want to inform the user about those issues. This is a screenshot from our beta version. It's not very nice, but it gives you an idea. It shows the important information. There is which problem was found on the device, which risk it presents to the customer, possible solution with some additional information, as we want to educate the users.
And this example is a particular vulnerability in ASUS routers, which unfortunately send out the current administration password in clear text in the HTML code of the page in a comment, or actually in a JavaScript comparison, pardon. And even if you change the password, it gets sent again to the client, and he can just look at the source code and type in whatever is there in that comparison.
You can read it in plain text in JavaScript.
Which translates to that message that hackers can easily obtain your administration password and gain complete control of the router.
So we have our security scanner, but there are some issues to address. You know, it's not a silver bullet. The first great problem we have is how to help users fix those issues we find. In many occasions, there is no fix available. In other occasions, the fix is available, but it's hard to apply. How can we help our users, for example, my mama, to fix the device if he has no knowledge about computer security. The other problem is reporting those issues. There are networks where we don't want to report our security breaches or something like that. Imagine free Wi-Fi's like in McDonald's or corporate networks. We are creating scanner for home secure networks, but it definitely gets around in different networks as well, and we want to cause harm, which brings me to the last point. We don't want to create a hacking tool, a user-friendly hacking tool, so we need to devise our scanner to help to protect, but not to help to harm.
The problem is that the probes we send are unfortunately of the same nature as the requests sent in actual attacks. This is unavoidable, but we at least need to design it so that we do not run it in networks where IPSs are present, so that our probes don't get flagged. And we also want to design a tool in such a way that those probes are of no use for actual hacking. And by that, it in fact means that those who want to hack will look at some other kind of tool and not use our scanner for that, because we can't stop them, of course. Now, in anticipation of a question from the audience that was sure going to happen, I would like to answer it first here. Have we tried contacting the vendors with this? The answer is no, at least not yet, because we have already seen the previous talks on device insecurity, and we have seen the results of those researchers. On last year's Virus Bulletin, there was an excellent talk by David Jacoby named How I Hacked My Own House. David was dealing with trampoline attacks, and while he eventually succeeded with contacting the vendors of the devices he found vulnerable, it took him quite the journey to get there, and he had to use his own personal contacts in the industry to get hold of someone competent at the company that made the vulnerable device. Others were not as lucky as David, and the vendors didn't respond at all. So that brings me to the final point of this presentation. Because me and Martin, we are young and naive, we would like to try and make an appeal to the security community here. We should stop just alerting ourselves that devices are insecure. We should alert those who actually buy those devices, because vendors care about selling them. Once they're sold, it's over. Those who have the choosing power of having a secure or insecure device are the users who are not even aware that device insecurity is a thing. If we all integrate automated scanners in one form or another into our security solutions, then we can at least try to exert some pressure on the vendors, but we can only do so by informing the users. If we mail the vendors that their devices are insecure, we are going to get ignored because we do not affect the sales. If the users start picking the more secure devices, then security becomes a competitive advantage. And when that happens, this cycle may start to be self-sustaining, and the global landscape of device security may start to improve. Until the users know that this is a problem, the situation will only be getting worse. And we can't blame the vendors, because they do what companies do. So we would like to thank the rest of our team at Avast, without whom this project would never have been possible. This was not a two-man show. So thanks, guys. And this is the end of the talk. So if anyone has questions, and we have time for them, do we or not?
You'll have to save them for the break, I'm afraid.
No. Okay.
But let's-
So